Even though the mean field theory is widely accepted in the statistical mechanics, and mean field theory itself is very rough approximation, and more sophisticated approximation is the Bragg-William approximation, and this Bragg-William approximation employed density matrix formalism and the thermodynamic variation principle, and it is more reasonable, more general argument for treatment of the Ising model. Here, I will start for the Bragg-William approximation. And this Bragg-William approximation is treated this theory, Ising model, by the density matrix formalism. And plus thermodynamic variational principle. What is the density matrix? Density matrix is also widely employed in the graduate level statistical mechanics, and I'm not sure you studied for the graduate level statistical mechanics, but in graduate level statistical mechanics, they deal with density matrix formalism, and the density matrix formalism is is kind of quantum mechanical description of the statistical mechanics, and therefore it is very fundamental mathematical formalism. And how to define, what's the definition of the density matrix is that in canonical ensemble, the probability of the system is in a state n, and the probability Pn is that the denominator is the partition function exponential beta epsilon n, and here numerator exponential minus beta epsilon n. It is a probability in the canonical ensemble. As I said, canonical ensemble only consider for the energy exchange, not particle exchange. In this case, the thermal average of an arbitrary operator A tilde, and thermodynamic average for A tilde is considered for the n is the state, and for the summation for each state, and it is n A tilde n. It is a thermodynamic average in quantum mechanical description, and also it is a quantum mechanical description, but we should consider for the temperature effect, and the temperature effect for the probability of the system. Therefore, it is that summation n exponential minus beta epsilon n exponential minus beta epsilon n. It is a thermodynamic average. And this denominator is the partition function. Therefore, it can be write down. It is 1 over partition function, and summation for n A tilde n exponential minus beta epsilon n. It is a thermodynamic average. Here we define that the density matrix by rho tilde is that 1 over partition function and summation for n and like this exponential minus beta epsilon n. This is the definition for the density matrix. We can say that if there is we can know that for density matrix at lattice side, then the total density matrix is that the product of the density matrix is the overall lattice side. For overall lattice side is a product for density matrix. Therefore, it is the case for the canonical ensemble. How about in grand canonical ensemble? There we can think about that. It is a similar argument from the canonical ensemble. Grand canonical ensemble we only consider for the exchange of particle, and therefore grand Hamiltonian grand Hamiltonian can be write down is that the Hamiltonian minus mu n tilde. Here is the n tilde means the number operator. Number operator, and the mu is the chemical potential. Yes, the mu is the chemical potential. Mu n is the dimension of energy. And also here, n is the, let's consider for the set of n is a complete set of eigenstate of the grand Hamiltonian. It is a grand Hamiltonian K. Then there can be write down as an eigenvalue problem, because grand Hamiltonian n is that eigenvalue, Kn is that eigenvalue of the grand Hamiltonian. This eigenvalue problem can be defined like this. In this case, the grand canonical density operator, the density operator in grand canonical, grand canonical density operator can be write down rho tilde 1 over grand canonical partition function summation for n exponential minus beta kn. It is a grand canonical density operator. The argument is identical, basically similar with the canonical density operator. And in general cases, the eigenstate is not well developed and well defined. And here in the eigenvalue problem, we can define this. The eigenvalue problem here can be easily defined, but in some cases, the eigenstate is not defined. And in general case, for the we can think about that V set of V another eigenstate of Hamiltonian. In the case that the state is not an eigenstate, even though, then here density matrix can be defined like this, and also V rho tilde V prime, here V, and it's one of a grand partition function, and V exponential minus beta k V prime, and it is like that 1 over g exponential minus beta k. Even though it is not a eigenstate, and we can write the density matrix like this. Therefore, in this case, the thermodynamic average of operator n is that 1 over g summation for each eigenstate, not eigenstate. And here, if it is eigenstate, expectation value for a tilde n and exponential minus beta kn, n is the eigenstate. But in this case, we should expand as a basis non-eigenstate basis, and for grand partition function for v and v prime, v a tilde v prime and v prime exponential minus beta kn v. Then here 1 over g trace a tilde exponential minus beta kn, and in other words, it is a trace a tilde rho tilde, and here the grand partition function is that trace Boltzmann factor beta k like this. You know, the normalization, from the normalization trace of rho tilde equal to 1. If you're familiar with quantum mechanics and statistical physics, and you can easily accept this concept. And anyway, I suppose that you accept this formalism for the density matrix. And anyway, and from this point of view, let's go on apply to the Ising model. And here we deal with for the Gibbs free energy. Gibbs free energy is defined by that minus s dt minus mdh in magnetic system. And in equilibrium, the variation of the Gibbs free energy should be 0 at fixed temperature and magnetic field. And also, therefore, this delta G, therefore it is a thermodynamic variational method. And here we deal with density matrix formalism. And the density matrix is approximated by a direct product of the density matrix for individual spins. And we say that the density matrix is that product of the individual spin density matrix, and also it is like that it is proportional to the Boltzmann factor minus beta hi in the canonical ensemble. And we assume that spin fluctuation are not uncorrelated, and do not consider for the correlation effect. And here, let's try the trial density matrix. Trial density matrix like this: 1/2, 1 plus mi, and 1/2, 1 minus mi. And off-diagonal component is 0. And why we write down is a trial density matrix, and it should at first trace rho I should be 1. Therefore, in the trace rho I is equal to 1. And also, and this term is a spin up, represent the spin up state, and the down component is a spin down state. And here we can think about that the density matrix should represent the spin up state and the spin down state in the Ising model. And anyway, then trace rho should be 1. And by considering two criteria, we can write down this trial density matrix. And here also, from the translational invariance, the magnetic moment is, let's consider a constant. And for each magnetic moment is constant by the trial translational invariance. From the trial density matrix, and we can think about that the trial entropy. From the average spin orientation is the magnetic moment. Average spin orientation. Average spin orientation is the magnetic moment, and is average value of the spin. And from the density matrix formalism is a trace and SI rho I. And also in here, in the Bragg-William treatment, also we adopted mean field approximation. In mean field approximation is that spin correlation, spin SI, spin A, Sj, and here we assume that we do not consider for correlation effect, and this spin-spin interaction can be regarded as a separated spin, Si and Sj, and also Si and Sj, the thermodynamic average is identical with each other, therefore it is m squared. And here, the trial enthalpy is that here let's write down as enthalpy like this in order to discriminate of the Hamiltonian, and it is a thermodynamic average of the enthalpy. And also it is that we know it is minus j summation for ij for nearest neighbor interaction, and Si Sj spin-spin interaction from the Heisenberg term, and the minus h for I Si, it is applying magnetic field case. And also here it is minus 1/2 is to avoid the double counting, and gamma is the number of nearest neighbor coordinate, and the j value, and n lattice sites. And from the mean field approximation, SISJ is that m squared, and therefore it is minus NHM, and it is a trial enthalpy. And the trial entropy in the entropy in terms of the trial, in terms of the density matrix formalism, it is like that, and minus KB trace rho Ln rho. It is that trial entropy from the graduate level statistical quantum mechanics, and it can be represented like this. And anyway, then we assume that it is a rho is the trial density matrix, and the trial density matrix is defined like this. Therefore, because there are n number of lattice sites minus n kb, and also, and the first term 1/2 1 plus m it is a rho and ln for 1 plus m of half. The second term is that plus 1 minus m half ln 1 minus m half. Therefore, we already calculated for the enthalpy and the trial entropy. Therefore, we can consider for the Gibbs free energy. And in the thermodynamic average, thermodynamic point of view, and Gibbs free energy is a fundamental property in basic thermodynamics. In statistical mechanics, and the partition function or the grand partition function is essential ingredient to calculate the problem. But in thermodynamics, free energy is essential ingredient for thermodynamics. Gibbs free energy is a starting point to solve the problem, and Gibbs free energy should be minimized. Minimum point in nature, all the system approaches to the minimum energy value, minimum free energy, not energy but real free energy, and therefore the Gibbs free energy can be written down Gibbs free energy is that enthalpy minus Ts. It is enthalpy plus kBT ln rho, because rho is the I'm sorry, it is not a ln, it is a trace. Therefore, here the enthalpy we calculated from the above, minus 1/2 gamma j n m square minus n h m, and from kBt plus n kBt and kBt is that 1 plus m half and then 1 plus m half plus 1 minus m half and then 1 minus m half. And the variation principle with respect to the magnetic moment at constant magnetic field and temperature, and therefore the derivative variational of the Gibbs free energy with respect to the magnetic moment, and it can be written down minus gamma j n m minus nh and plus n kBt, and also the first term, the differentiation first term is that the 1/2 ln 1 plus m half, and second term, this one second term is minus 1/2 ln 1 minus m half, and also and the derivative of the ln is that 1/2 2 over 1 plus m, and cancel with each other, and therefore, and also here the derivative with the ln term is that plus 1/2, and the derivative of this ln term is that minus half. Therefore, it should have the 0 and equal cancel with each other, and also we can summarize this value, and therefore let's write down 1/2 n kBt at n, anyway, and at n over 1 over 2, at and half can cancel with each other. Therefore, it is 1 plus m over 1 minus m is that gamma j n m plus nh. Then at n 1 plus m over 1 minus m is that the 2 n cancel with each other in both sides, and the gamma j m plus h over kbt. Therefore, 1 plus m is that 1 minus m exponential 2 beta gamma j m plus h. Let's write down as the beta gamma j m plus h as x. In this case, here let's summarize as m 1 plus exponential 2x, then exponential 2x minus 1. Therefore, m is that exponential x minus exponential minus x, and exponential x plus exponential minus x. Therefore, it is a hyperbolic tangent beta j gamma m plus h. The solution is identical from the mean field theory, and anyway, it is from the density matrix formalism, and it is Bragg-William approximation is the same solution, and m value and here hyperbolic tangent. It can be also calculated by the numerical solution, which it is identical result from the mean field Hamiltonian. But anyway, and this kind of density matrix formalism is more general comparing with the mean field theory, and it's supposed that there is a finite phase transition without magnetic field. It means that the spontaneous magnetization can be possible in the Ising spin system. But in the next, I will describe an exact value, exact solution for the Ising model, and the exact solution is very difficult. Anyway, one-dimensional can be easily calculated, and the two-dimensional case is extremely difficult, and Angsaga also awarded the Nobel Prize, and also we do not consider for the Angsaga solution. It is another very difficult problem. And anyway, and here I will conclude the Bragg-William approximation.